the idea of this week is, so this will be my last lecture, well, it's last lecture in a little block, so Matt comes back next week. I return in a few weeks' time after that to talk about convolutional neural networks. But so this will be the last thing where I talk about sort of like traditional deep learning. So talking about neural networks in their sort of vanilla standard form, and talk about all of the things to think about with old school deep learning. So I'll talk more about unusual types of signals, convolutional neural networks, and different types of, slightly more modern types of deep learning next time. And then Simon will go into transformers and all the other new goodies after that. So, one more week exploring traditional deep learning. I think the really nice thing about this is there's a few different topics. So these error sources, the bias-variance trade-off, and then we'll talk about regularisation towards the end. But this I think starts to get at some of the big mysteries or some of the big ideas about deep learning, which is really all about. This comes back to one of the big ideas about deep learning that I talked about last time, and it's this idea of generalisation. So why does this deep learning, this crazy paradigm, where you have this structure of neural network, composition of functions, then linear things that are stuck in non-linear things, then you do some optimization to come up with a deep model. And then the big mystery about it is it happens to generalize well. So it happens to work well on unseen data. And that is a mystery why that happens. The answer has something to do with regularisation, I think, and we'll focus on this and we'll prod at this today, and we'll start to get a bit of a feeling, I think, at least for me, as to why this works and what's going on. So the central thing is there's a nice big mystery called double descent that I'll get to in an hour or so. And then you'll hopefully get a bit of a flavour, a bit of a feeling for why that works. I think the answer partly lies in regularisation, and then we'll explore some of the hacks that people do to actually regularise these things and make them generalise well. So that's where we're heading. Before I get into that, where this all comes from. So the big rewriting that I did of this was flipping from cobbling together stuff from research papers, from old books, like pattern recognition and machine learning by Christopher Bishop, and then some kind of good but awkwardly worded chapters from the Goodfellow Bible, and then I sort of replaced it with a deep dive into chapters 8 and 9 really, from this Simon Prince Understanding Deep Learning book. So most of the stuff I'm going to talk about today, you can read these chapters and understand yourself. Actually a really good book. As I've been working through it, I highly commend this book to you. Okay, so the generalisation problem is where we're going to get to, and what we're going to focus on here. So, last week we played around with optimization a lot, and we've played around at this stage with MNIST and training a deep learning model to predict the digits in MNIST. And one of the things that you see is people train these things forever, right? So the first interesting thing that you see is that people feed the data through this model again and again and again, and just keep doing stochastic gradient descent. So there's nothing to stop you looping through all of your data again and again as you're estimating the gradient in stochastic gradient descent and heading downwards in this cost landscape. So you can train this thing forever and ever and ever. And you've noticed that the model gets better and better, at least on the training data set, as you train it and train it and train it and train it. And we talked a bit about that last week. Some of the intuition for that is sort of a flat cost landscape. You're trying to fall off these cliffs down to down to these manifold minima, and you sort of can keep doing that. There's a bit of a problem here. So you can train and train and train, and you find that you get happy because this loss function that we keep looking at keeps getting smaller and smaller and smaller, right? We get better and better and better. But then a bad thing happens if you have kept track of this. You keep doing this for a really long time. One thing that you find is that the test error. So this is like the accuracy measure. After a certain point, the model doesn't do any better, doesn't get any better at predicting unseen labels, or plateaus there. And even worse, I think that you can see if you were to look at the loss function actually applied to the testing data, it can go back up. It can do this bad thing. So there is this bit of a problem in the practicalities of doing machine learning and training these models, which is that you have diminishing returns, right? And in fact, you can get kind of worse in some case. So you sort of wander around this cost landscape, but it doesn't help you, and it makes it actually worse on the problem that you care about, which is testing on unseen data. And you all probably at this stage have an idea of why that might be. The related thing that you're going to be worried about is the problem of overfitting, right? So the problem that we have with deep learning is that it's a model with lots and lots of parameters. We talked about this in the first week of this module. Heaps and heaps of parameters, and so the obvious problem that can happen there is overfitting, right? So as so this is not a deep learning example. This is just a polynomial regression model. So a 0th order polynomial puts a straight line through these data points. That's a bad model. First order polynomial puts a straight line, also a bad model. A cubic model is pretty good. They've got 4 parameters or something like this. We've only got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 data points. So a 9th order polynomial fits through those perfectly. Right. But if I take other samples from this truth here, add some noise, then it's not going to fit those at all, of course, because it's not actually a 9th order polynomial, and so the test error goes up. Right, so it's the same sort of idea as the capacity of this model, or of the number of parameters in the model, gets better. I can do better and better and better on my training data set. Can get it to fit my training data perfectly, but then that's got no predictive value at all. Sort of similar sort of idea that's going on here. Surprisingly, a deep idea. I may have been in conversations with professional people in recent weeks who don't know these things. So this is not trivial by any means, but for us it's pretty easy to see what's going on here, and this is a bit of a problem with this whole paradigm. The mystery of deep learning is that it actually can still work, and I'll show you something that's more surprising than all of this later on. So this is what I want to explore today. So big question is how we get around this, what we do here, and why deep learning doesn't so much suffer from this problem, and why it can still do well, even though it's arguably a very overfit model. There's heaps and heaps of parameters, and it can go crazy. So to do that, I want to base most of this. So this is the Simon Prince thing. He has a nice toy example here of a really simple one-dimensional problem encoded as a neural network. So let me describe what this is. So there's a sinusoidal-like, sine-ish sort of true model here. And then there are some training data points, yes. So I have some noisy training data points from this true black model here, and we're trying to recapture that black model. And then the model that we get that's going to get fit here, to try and recapture this nonlinear sinusoidally type thing, is described by this neural network where I've got 3 activation functions here, and those activation functions are all going to be ReLU type models. So this rectified linear unit, so it's negative, so it's 0 for any negative value, and then it's just y equals x for anything positive. That's what this means. I'm trying to predict the y values here. So I've got 3 activation functions. We'll constrain it even further, and we'll let them take only specific formats here. So we'll have 3 shifted versions of a ReLU function. So this is the origin sits here, so 0, 0 sits here, and so this is a ReLU function 0 to the left here. It goes like y equals x, like that, and then we'll have a shifted one here. So we'll only have a piecewise function that's 0 up to, I think this ends up being 1/3 here, and then rises linearly, and then another one 0 up to 2/3, and rises linear. So they're shifted along in just piecewise ways. If you think about it, that's the same as having a linear transformation on my data. So having an ax plus b type transformation, and then feeding that into a traditional ReLU, right? We're essentially just constraining it to having a shift of 1/3 and a shift of 2/3 here. So it's a more constrained version of the neural networks that we've talked about. So what's the effect of having? So you can also just think of this as a linear combination of these 3 activation functions here. So what are some examples of the functions that can come out of this? That would be these 3. So they're going to be piecewise linear functions that we get out of this, right? Because my activations here is H1, H2, H3. They're all linear. I'm just adding these up with different gradients. So like this, let's look at this one. So this function will be sort of this shifted downwards. This would get down here. I'd have to flip this one around. I'd have to be subtracting off here. So multiplying this by a negative, so it goes down. So be able to construct it going up and then down. So I can create families of functions that look piecewise linear, right? And they're going to, hopefully we can kind of get them so they go up and then down and then up again, something like this. Does that make sense? It's the sort of architecture of this thing. I can go even a little bit. Here's something that you should do. If you go, actually it was just there. So if you go to the course GitHub, go to the website for this, and scroll down. So this is on chapter 8. There's a handy little notebook here, which will eventually open up. You can actually look at the code that was used to generate this. Let's generate some random points, and then we'll actually fit the function, or plot the function and the data in the uncertainty, right? So so you can even look at my true function here was that. There's a sine function. It's got an exponential in it, so it's a bit squished. And then I can even go and you can actually fit the model, right, in a prediction. So my training data was the red points. I can fit the cyan thing, and it looks like that. And you can dig into the code. So this is kind of interesting because this is so simple. The structure, you can actually solve this exactly. You don't actually need to do stochastic gradient descent because there's only one layer in this neural network. If I come back to this, right, there's only one layer here, right? So I do a linear transformation. I feed through these ReLU functions, and then I match it to my output. You can actually write that down as a least squares. So if you write down a least squares cost function and set up the design matrix correctly, you can actually solve it exactly using linear algebra. So there's the linear algebra that's getting done. And yeah, the least squares solution was the form, some design matrix A transpose times A, take the inverse of that, times A transpose times B. Does anybody recognize that form of combination of matrices? Yeah, where have you seen that before?
For beta hat?
Yeah, for beta hat, so for linear regression, right? If you want the maximum likelihood estimator for the parameters in linear regression, it has that exact form. So the only difference here is that we have a different A matrix. You can go look at this and think about why it looks like that. That's the ReLU bit of this, right? If these values are negative, then we zero them out. So that's a ReLU going on there, and then this is a piecewise linear. That's a way to get piecewise linear bits out here. So you can look at that and play with that. And it's actually nice that this actually all works in a regression type framework, and we can do everything exactly here. It's a good exercise for you. Okay, so I've belabored that because I'm going to show you a bunch of photos, a bunch of pictures of this function and these different types of model fits now for the rest of the lecture. Does this make sense, what's going on here? Cool. So I'm basically approximating this nonlinear function with piecewise linear functions. And that happens to be, you can write that down as a neural network. So rad. So let's think about where are the sources of error here. So if I'm going to fit one of these piecewise linear functions to my data set here, where can error come from? So where can I make mistakes? And it turns out, and I'll demonstrate it on the whiteboard in a sec, that there's three sources of error here. So the first source of error is just from noise. And so noise here means I've got some testing data, right? So I've got some data that that is supposedly drawn from the distribution, some data that represents this true underlying model here. But that data is noisy, right? So it doesn't, by noisy here, it just means it doesn't lie exactly on the true model. Something like MNIST, it doesn't necessarily, an image doesn't necessarily perfectly map to the digit that it corresponds to. There's just some noise there, right? So that's just inherent in the data that I have, right? Some data will be noisy, some data will be crap, won't look like anything like the true model. This data's not so bad. So the next thing is bias. So obviously, I'm trying to fit a curvy line with three straight lines here. Right? So my straight lines will never be able to capture the curvy line. We'll never match it up perfectly. So no matter what I do, you can see there's going to be some gap here, and there's going to be some bias. That's in the Georg picture when I started with, that was called approximation error, but you can think of that as just bias. It's just the straight lines will never be able to capture the true model perfectly. And then there's variance, which is that, and the idea of that is that I have some training data here, right? And I'm trying to fit that model, I'm trying to approximate this black line by fitting my straight lines, my cyan lines here to these orange data points, right? So I don't have the true data. I've got some noisy training, data, and then depending on the quality of that training data, I'm going to be able to fit different models. There's going to be some variation in the models that I get out, and so that's being captured by the lines here, or the shading here, is meant to represent that if I have lots of different training data sets and fit the best model that I can to each of those training data sets, then they'll all look, they'll all look different. So there'll be some variation in those. That's variance, and then that's it. So what I want to do is spend a little bit of time. I'll make that a bit more precise. yeah, well, basically, yeah, what I'll do is I'll explain why that's everything here. That's all the sources of error that we have. So another whiteboard thing. Nice little argument. Again, this is all in the summary principle, so you can go look it up. Okay, so let's see. So we've got 3 different things. So we've got observations, to write down some notation. So we've got observations y, they're a function of inputs x. We'll say they're drawn from some distribution, right? So there's some drawn from some distribution that has a mean, that I'll call the expectation over y of y of x. So we'll assume that there's some distribution that I'm drawing my y's from, and this means taking the expectation over all of those observations. So you know, the sum of the probability of y times y. Add that up over all possible y's. That's what this will be shortened. And we'll give that some variance. Some variance sigma squared. I don't need to say anything more than that. I'm not going to specify whether this is normal or anything else. I'll just say that there's some process that generates observations, which has some mean and some variance in the process. What else have I got? I've got a model. Right, the other thing is I'm trying to fit cyan lines. So my model output, I'm going to call that F, and the model output depends on X, right? So it depends on the inputs. So I've got a neural network, right, that takes in X's and spits out Y's through this crazy structure, through this crazy piecewise structure. But it also has some parameters associated with that. So you know the slope of this, the slope of that, the shifts and things like that, and all this stuff. Does that make sense? That's the setup. So let's say, let's just write down the least squares loss function. So least squares loss function here would look like the difference between my model outputs and these observations squared. Straightforward. Okay, let's do some manipulations so that I can do some math. Let's try and work this mu in here. I'll work it in by subtracting a mu and then adding a mu. And I'm immediately going to drop I'll drop the x phi, I'll drop these x's, I'll drop the mu of x. And let's just assume that they're, let's do that. Okay, so do one of my crazy stupid math trick that statisticians always like to do. And why did I do that? Because now I've got squarey type things that I can expand. So I've got 2 things squared plus 2 times just expanding it. And now, you know, this depends on my observations, right? So this loss depends on the observations that I have here. So I don't really want the loss. I want to say something general here. So I actually want to take the expectation of this over all my possible observations, right? So I said these observations are drawn from some distribution with some mean and variance. So let's take expectation over that. So that's expectation of everything here. So the expectation of that plus the expectation of that plus the expectation of that. My expectation is over y, but there's no y's, there's no test observations, there's no test data in this. So that doesn't change. Alright. Similarly, the expected value of this times that, well, I can take the expectation immediately inside this bracket here. The expectation of mu is just mu, then the expected value of y is going to be the expected value of y. So that's just using linearity of expectation, I guess. And then this is a squared thing, so that's kind of a bit trickier. I better leave that is. For the moment. What simplifies here? What disappears?
The y of y is just mu, so that term disappears.
Yeah, that's 0, right? So the expectation of y with respect to y, I just define that to be mu. That mean, so that's mu minus mu. So actually all of that's equal to 0. Anything else? What about this? It does look like a variance, because it is a variance. Yeah. Well done. Yeah, that's exactly, that term is exactly the variance of y. That's where I wanted to get to. Cool. All right. So we've gotten somewhere useful. At this point, actually, let me just replace in my x's and my thetas. Take away mu of x, and then sigma squared will be a constant. So now, actually, so there's something else here. Right? I said my model is a consequence of the parameters that I feed into it, right? So I've written those down explicitly. But to go even a bit more than that, the specific model that I get out is actually dependent on the training data, right? So, theta depends on my training data. We'll call that D. So actually, fairly, I should make note of that here. I should recognise that the parameters that I get in my trained model depend on the training data D. And actually, there's some noise generating, that means they're noisy as well. They've been drawn from some underlying distribution. So, I can think about the expected model output. So if I think about taking expectation over my data set, right, I really should be thinking about this I think I've got it up the right number of brackets there. I'm going to call that something, I'll just call that F subscript D as I call this. Well, I didn't actually call that anything. Alright, so I'll think about the expected model output, the average model output over all possible training data sets. Okay, so I'm introducing this, taking an expectation over training data. This is up here, I took an expectation over testing data for output data. Right? All the data is noisy, so think about that. Does that make sense? Okay, so I've introduced this now, this FD. So I can go a bit further here. Let's do the same trick as I did up here. This is like a people would call these Gary-Glonick tricks, right? Like you add something and take it away, so that you can go a bit further. So I'm going to subtract this FD thing. And I'm going to add it in again. that's just subtracting and adding. So that I can square things. And then I'm going to expand this out again. So we'll do squared plus 2 on that. So this is where all of our eyes start to glaze over a little bit. And so you can check and make sure I'm doing the right thing here. Because I didn't before and confused myself. I think that's right. Okay, take a wild stab at what I'm going to do now. So that was just algebra. Why did I do the crazy thing? Happened to be exactly the same crazy thing I need to get from there to there. Right, so going from there to there, I subtracted and added, then I expanded out. Then what did I do?
Got some things equal to 0.
Yeah, I got some things equal to 0, and how did I get them equal to 0? By taking the expectation over y, my observations. I've now introduced the idea of an expectation over my training data, so let's do that. So let's average over everything.
So you're averaging over testing and training?
Yes. So this is really the expected model output. So what's what here? So I'm taking the expectation of this quantity. That's going to stay, right? Because this is a variance type term. What's that? This term hopefully disappears, right? We kind of want this term to disappear. Otherwise, what the hell am I doing with all this? If I take an expectation over D, does that disappear? So I only need to take expectation over things that have D in them, so that doesn't have a D. That's already got a D. That's that.
So the first one, the first term?
Yeah, so that term, if I take the expectation over my data set on that, well, I mean, it becomes that, which is that, right? So actually those two things are exactly the same. So that term there goes to 0, and so the whole thing goes to 0. So exactly the same trick as what happened just on the other term. This term stays. Where does that term stay? Oh, well, it's already, taking the expectation over this is just the same thing. It's like taking the expectation of a constant, right? Which is what I want. And taking the expectation of a constant is that. All right, cool. We're done. So let's look at this. So what do I have here? I have a variance term, right? So the variance of my model with respect to the training data. That's what this is. Right? So what is that? That's this. Right, so the orange dots are my training data. The idea is that there's some distribution. They've got noise in them. They have some randomness. They live in, they live on as outputs from some sort of stochastic process, stochastic model. And so that's that term there is exactly writing down the variance in my model over the training data. What's this one? Well, this is, the expected model. That's the difference between the expected model output and the mean of the observations. So the mean of the observations, I mean, if this is if these observations are actually centered on this black curve, then the mean of the observations is that black curve. Right? And what's f of d? What's the expected model output? Well, it's one of these piecewise functions like this. So that actually is exactly my bias term. And what's the remaining thing? Well, it's just a variance of my observations. So that's literally my noise term. It's the variance in that. So when I say there's three sources of error in this process, the noisiness of the observations, how good or bad my observations are, my test data is, the bias in my model, the ability of my model to capture those observations, or to describe the truth here, that's the bias, and then there's the variance that you get from having noisy training data. That's it. And actually here they add up additively here. So yeah. So when I say there's three sources of error, there's sort of provably three sources of error. Okay, right? So if we can understand each of those sources of error, then we're sort of done here. Let's see. So the first thing to say is there's not much we can do about this one. Right? We're given some. We have some test data. Right? There's not so much I can do about. The noise in the truth, the noise in the climate, or noise in the fundamental system that I'm trying to predict. So we're a bit stuck with this. The only ones that actually involve my model, right, the model that I'm actually trying to train here, my imperfect model, are the bias and the variance terms. So the fact that I don't have perfect data sort of limits me there, but I can think about the bias and the variance. So okay, so how do we reduce error here? And so let's just focus, I'll come back to these ones later. But there's a couple of things that we can do here. So maybe I'll talk about these. Yeah, I'll talk about these. It won't take that long. We might have a break 5 minutes after the hour. That's okay. Okay, so variance. So what's variance? So that's the variability that I get from having noisy training data. How do I reduce training data? Well, get more training data. And actually, the quote here is a guy from Google. So this is reminding me of I was at the World Wide Web conference in 2015, 2016 or something like this. The World Wide Web conference, WWW, is a very famous computer science conference. Happens to be the conference that PageRank was introduced at. One of these big conferences. There was a guy from Google there who was actually chatting to at some break or something like this, and we're sort of talking about the difficulty of doing machine learning, generally how you build better models and things like this. And being from Google, he said, well, if you want a better model, then just get more data. And I was like, sure, mate, you're Google. You've got plenty of data. We might be talking about, I've got 100 observations of, flu or something like this that I've collected from GPs or something like this. Can't just go and get more data for everything. I can't infect more people with influenza. Just get more data for the models. They're easy for Google to say, but you can get more data. That's the first thing. Bias. We need to go deeper. How do you improve the bias here? Well, if I was not just being so crap as having 3 straight lines here, and if I had 10 straight lines or something, probably I can get a bit closer to approximating this thing. There's the sort of general ideas. So let's actually look at how they work. So reducing variance would look something like this. I think what is going on in this picture is I've got 3 samples of the same thing. So here I've got 6 samples, right? So 3 random samples from this model. So they're all centered on this. All the training samples are centered on the true models here. but they're noisy. We've got 3 different realizations of that. And then I do 10 samples in this column, and you can see that whereas this model's pretty garbage, and this model's pretty garbage, this one's better, and this one's better. And if I've got 100 samples, then these get better and better again. And so they're 3 samples, and then on average, what happens, so you do this now 10,000 times, you generate 10,000 training data sets of all these different sizes, fit the model, and you can do that really nicely and easily with the code. It's online, so you should play around with that. Then if you look at the envelope of all of these straight lines, high variance, getting lower and lower. So again, models that have lower and lower variance. Cool. What's the problem with that? So I've gotten more and more confident about my model as I've gone across here, right? But what's the problem with this model?
Bias.
Yeah, well, I was thinking more like, it's shit. Yeah, that's a nicer way to put it. It's a crap model, right? So it can get as confident as I want, and you can see that between 10 samples and 100 samples, this model's on average not changed much from that. It's not really changed much from that even. I've just got more and more confident about it, even though it's crap. So yeah, a misspecified model is what psychologists might say. It's a bias model. It's just not a very good. There's model error, is what a numerical weather prediction or a climate modelling person might say. But it all means the same thing. Right? You can't get a curvy line.
When you say misspecified, you mean just by virtue of trying to fit a nonlinear function with a piecewise three linear.
Yeah.
So you're sort of doing as well as you can, provided your intention is to fit 3.
Yeah, as long as, provided your intention is to do something that's impossible, and so this is about as good as you can get, right? And so you're just getting more and more confident to something that's not going to get any better. So what do? Well, more straight lines, right? Kind of an obvious idea to math people who have seen Taylor series and stuff before, right? But yeah, you can increase the number of regions here. So machine learning people would say this is increasing the model capacity. As we come over here, it's reducing the bias. And basically, instead of allowing 3 straight lines, here I'm allowing 5. Right? Here I'm allowing 10. And then it's no surprise, I guess, that gets closer and closer. So those models get better and better. So that's the other thing. So there are 3 realizations up the top. And again, same sort of story as the last picture. You do the same thing 10,000 times or whatever, and then look at the envelope of all of these straight lines that you get, and you get these pictures down the bottom. So what's the problem here? Looking at these ones now. What's upsetting?
The variance.
Yeah, the variance is crap, right? So I'm leading you to something which many of you have seen before. Right, so here, these models got more and more biased, got more and more confident about their bias. These models are getting less biased. As you come over here, that's a good model, but it's got higher variance. What are we trading off here? The bias and variance. Right. So you can kind of see that from that's kind of encapsulated in here, right? These things add together, and that is the essence of the bias variance trade-off. So let's see, what are we illustrating here? This is increasing the number. This is increasing the capacity here of the model. So the number of piecewise sections, you can see that's going up and up and up. So we're fitting the training data better and better and better as we go here. But you know, that model's not so bad, right? But this model's pretty, it's not very good. It's not capturing the true distribution. So yeah, so as you increase the model capacity, increase the number of parameters, so the number of segments, the number of straight lines, decrease the bias, increase the variance, and so really what you need to do to get generalisation is to live somewhere in this, to look at them both together and be somewhere in the middle. So there's an art then to choosing this. Okay, let me say my last thing, and then we'll take a break. We'll talk a little bit about regularisation, and we'll have a play with something. Okay, so that's the bias-variance trade-off. Now, here's the exciting thing. Here's the picture that I started off with again. So here is this training and test, right? So increasing the number of parameters, increasing the model capacity, the number of hidden layers, so increasing the number of parameters along the x-axis for a few different data sets. We really want to look at these three, where there is noise in the labels, right? So where there's sort of imperfect, this is more like real data. So MNIST 1D is kind of cool. You can check it out. They basically take, I think I have it. I can't find it quickly. They take MNIST and they basically reduce it down to a bunch of like straight lines. So instead of having grayscale images, you have 0-1 images, you have black and white images, and you just have one line. They also reduce it from being, 200 by 200 or something, pixels down to being 20 by 20 pixels, so you have 400. You have 40 very low resolution straight lines that are just 0-1. So it's a simplified version of MNIST. And so you see this problem. When you train, the training error gets better and better and better as you increase the model size, but then the testing goes back up. Right? Same thing with MNIST. So this is our data set. This is another image data set, and you see the problem that we've seen. These dashed lines are the number of training items in the data set. So like 50,000. There's like 50,000 images in MNIST. So the testing goes back up. All right, now you ready for this? What happens if we keep going? Right? So we keep going past training these deep learning models past the number of this point of overfitting where we can get perfect accuracy on the training data set. What do you think's going to happen here? You should venture a guess at this because the title of this slide is Double Descent. Everyone's too afraid to search, so I'll just show you. It's quite stunning, actually, if you think about it. So what happens we know MNIST at this point. So we get to the point, we train deeper and deeper neural networks, deeper and deeper deep learning models, so more and more parameters. We are overfit at this point. We can perfectly describe the training data, and that's why the testing, the training error is 0, or very close to 0 in this. My model is bad at that point, right? It does badly on the unseen data, but I keep going, then the model gets better again. Right? So it does that in all of these, and it gets better again beyond the best that it was in this sort of bias variance trade-off traditional statistics realm. So I'm going to give you this in your assignment. I kind of want you to do this yourself, right? And see this. So pick a few points on this and reproduce this. This is shocking, right? You should be freaked out by this. Right? This goes actually against everything that we've learned in statistics. So why does it do that? how could this possibly be? Any hypotheses? Should I let you think about it for 10 minutes? Let you study this. Let's take a break for 10 minutes. And in that 10 minutes, try to talk about this problem. Think about what might be going on here. And then I'll try to explain this in the second half of the lecture in 10 minutes ago. 10 minutes or so. Good to think about it with this. You can think about it with this example. Talk to your friends about that. And we'll come back in 10 minutes and think about it.